last time, we talked about the Evans diagram, right? And the Evans diagram looks like this. So we talked about the Evans diagram last time. So the Evans diagrams look like this now. This is the potential in volts. Okay. And this is the current density in amps per meter squared. Okay. So this experiment, okay, is you set the current density, yeah, and you increase it linearly, right, and then you measure the potential response, right, and you generate this curve, right. So this is the anodic and sorry, this is the cathodic curve. This is the H2 evolution. Okay? And this could be any, but here, this is the case for the oxidation of iron. Okay? At P plus 2 electrons. So this hydrogen evolution is H2, what is it? H2, 2H plus 2E minus goes to H2 counts. Okay? So this is the 5 curve, this is not a curve. And so So you do the hydrogen evolution. You had the cathodic curve first, right? And then you do the knot. Okay. So what they intersect, right, is the B chord. So this is the B chord, and this is the I chord. Okay. So this is corrosion potential where they intersect, and underneath the point of intersection, if you draw a line down to the x-axis, okay, it is the corrosion current density. Okay. So using this evidence diagram, okay, using the evidence diagram, what can we get out of it? Okay. What can we get out of this? Okay. So we can just read from the plot, okay? And attempt to follow, okay? So question one is, what's corrosion potential? Okay. Just read over it, okay? Minus 0.54, okay? Minus 0.54 volts. Question two. Is what is INET at B chord? Okay. So the significance of this B chord, right? The corrosion potential is the potential at which the anodic and cathodic current density is the same. Okay? So at B chord, I current is equal to IA, which is equal to, so if these are the same, right? Then INET is equal to 0. OK， 这两个线交汇是这点，是吧？因为这是一个正极的范，是吧？然后另外一根曲线它是一个负极的范，是吧？一个是在放电，是吧？它在放，每次放是放两电，另外一个是它每次吸收这两个电，是吧？所以这边放的电跟这边接纳的电，在这点上是一样的，是吧？这就导致呢，这两个是相同，是吧？R 在这个点上放多少电，它就水里面的这个氢离子就拿多少电来做吸氢，是吧？所以这导致它 INET 等于0，在那交互点上 ，OK。So question 3. So what is the current due to H2 evolution? So the current density due to evolution, hydrogen evolution that occurred at B chord is, if you draw a line down to the current density axis, you get 136 amps per meter squared. And this is the same. So IA, IC is equal to that, which is equal to IA. Okay? Which is the same for iron to solution. Makes sense? Right? Because 在它们交汇点上，它们两个反应必须是相同，是吧？Okay, question 4 is, what is the over potential for a phenolic reaction at V core? So, so the equilibrium potential, okay, which is this dotted line, right, is at minus 0.68 volts. Okay, that's the equilibrium potential for iron. Okay. Okay, so if you put a piece of metal, okay, a piece of iron in the water, right, that's the potential that you have. Okay, that's the equilibrium potential. Fine, okay? So, the over potential, right, is simply the difference between the two, okay? So, V core minus U bar. V core is equal to minus 0.54, right? 0.54. Minus negative 0.68 volts. Okay. So this is equal to 0.144 volts. So this is the over potential. Okay. 也就是你把一片铁片放到水里面的时候，它所产生的这个over potential。So, so because corrosion is a phenomenon that we're a lot of us are concerned with, okay, we would like to have methods to measure experimentally corrosion rates, okay. So, methods for measuring corrosion. Okay? The simplest way to find corrosion or characterize corrosion, okay? The first way is barometric. Okay? 你把一片金属放到水里面去的时候，是吧？由于它金属的表面作为一个就是 uniform corrosion 的一个受害者，是吧？那金属本身是有阳极跟阴极的一部分，是吧？所以 这所导致的是它的 IC 和它的 IA 是一样的，是吧？所以你测不出来它电流的变化，你测不出来。一个方式呢来测，就是评价这个一片金属在水里面的腐蚀，最直接的方式就是靠重量，是吧？因为它腐蚀以后，它的金属会脱落，是吧？腐蚀成形成这种某种金属离子进到水里面去后，这重量会下来。So the first method to measure or characterize corrosion is by weight. Okay? To measure change in weight. Change in weight. Okay? So change in weight is equal to weight before minus weight after. Okay? And so we have time, right? Change in weight and change time. Yeah? So corrosion rate equals change in weight by change in time. 这是最直接的方式，是吧？So another method to characterize corrosion, okay, is what we call linear polarization. Okay, this method is used. This is more common. Okay, it's very common. Okay, so the setup's like this. Okay, you have a working electrode and counter electrodes. Okay, so you have the working electrodes like this, the counter electrodes like this, and you have a reference electrode. Okay, so this is a reference electrode. Okay, so this is the setup. Okay, so you use CSI, use some sort of potential stat. Characterize very small perturbations of delta V versus delta I. Okay. We characterize delta V versus delta I. Okay. Very small perturbations. Okay. And you get a outcome that looks like this. So this is so for the case of iron, right? You know the potential, the corrosion potential is around 0.54, okay, minus 0.54, okay? So this is I amps per meter squared. This is potential. This is volts. Okay. So you do small perturbations. Usually around like, you do analysis around like this region, okay? Okay? So you, like, this is like 10, 1, 1, 0, 0. So it's, so you get a curve that looks like that, okay? So, so we're interested in these regions, okay? These linear regions, okay? So, we're going to assume table kinetics. So, table kinetic just means that the relationship between voltage and current density is linear. Okay? So assume like linear kinetics. Linear voltage versus okay. So the expression looks very similar to the Butler-Roman equation. Okay. I chord times exponent alpha A and RT. So the Butler-Roman equation, okay, 那些你们没有上过上学习的课，我们是推导过这个 Butler-Roman equation， 从热力学开始推导。So the Butler-Roman equation looks like this, okay? So this is the corrosion equation, okay? The Butler-Roman equation looks like this, okay? It's very, very similar. I'm just going to write it here for you to see, okay? So, I is equal to exponent alpha AF RT S minus exponent alpha CF. So this is the difference between the Butler-Roman equation and the corrosion equation. Okay, this is chapter 3. This is chapter 16. This is very, very simple, and they should be, because they're both like equations relating the voltage versus the current. Okay, whereas previously, the Butler-Roman equation has like change in potential. Now, here on the corrosion equation, we have a B chord. Okay, we just have an additional B chord, and then in terms of the exchange current density, we have the I chord. That's the only difference. So, for small, change in V minus V core. Okay. We get a small delta down, right? 如果这个是小的话，这个就会小。 是吧？是主要是用在小范围内的这种就是这个震荡，是吧？So another way of writing this equation is I is equal to exponent ln 10 dA. V minus V core minus exponent ln 10 dC. With VA equals to ln 10 RT alpha So this equation is only valid for uniform group. Okay. So this equation right here is the basis, okay? This is the basis for the linear polarizations. Okay? So this is 16.7 B. So 16.7 B basis for linear polar polarization.我们实验室也是叫这个极化曲线，是吧？极化曲线测试。So if you linearize 16.7 about 这是一个直线，是吧？这是一个直线，是吧？ So if you linearize like this equation, okay, then we get a equation in terms of I is equal to I core So, this term right here, okay, is RP, okay, is 1 over RP. Okay, so you linearize this, okay? This is your X. This is Y, okay? This is slope. This is Y x. Okay. So this term right here, RP is the polarization resistance. Okay. So this term right here, right? This here is constant, right? Okay. So this is a constant. With the unit of ohms over meter squared. So if the with alpha A, alpha C, okay, the table coefficients. This helps. Okay. Then we can use, you get EA, BC. Okay. So with BA and BC, So if we know these, alpha A, alpha C, yeah? If we know these two terms, okay, we can calculate B and B C. Okay. Okay. If we know these terms, if we know this, we can get B A and B C now. And because everything else is constant. Okay. Once you have B and B C, right? Put it here. Okay. You get I4. Yeah. You can get I4 from I4. So I4 is equal to BA is natural log BA equals BC. Okay? Yeah? So this is the linear correlations, okay? So it's a quick way to get corrosion current and corrosion potential, okay? Using a potential step, okay? 这可以推导出一个就是腐蚀速率。用这腐蚀速率的话，是一种最常见的方式来对比，就是不同条件下的这种金属的腐蚀，在某个特定定点。你们有开始看书吗？你说我什么书？这个第16章。我没有。你们有看吗？没有看。你听得懂多少？一半是吧？那你呢？你现在懂多少？这是后面的。你现在懂多少？啊？多少？3到50是吧？那你们现在懂多少？啊？40是吧？瑞婷现在懂多少？3、4成。3、4成。余正。你呢？也差不多。你听了多少？
也差不多吧。
有什么东西老师可以做的吗？我非常贴近，就是这个书里面的东西。有什么可以做？你们上过我的史考，我看了你们反馈啊，就是有什么可以做？跟我讲。现在还刚开始对吧？如果现在跟我讲的话，后续的时间里面应用到这个时间会比较长。有什么反馈？现在跟我说。能做什么？讲话大声一点。我已经带上麦克风了，还不够大声。会吗？
是我的话，我可能会比较需要多一点听中文的部分。 就听英文可能还
这
是
课要求
对
必须在70%以上，
对，
所以我如果讲太多中文的话，就是
就也没办法。
对，还有别的呢，就是我尽量的就是能讲中文的时候我就讲，是吧？还有你有什么说？我写的东西你看了吗？我还会太吵。
你那个写 R 跟写 B 的时候，可以写清楚一点。
这个是吧？
不是，像是下面那个 polarization 那个 R。
这个是吧？
对，就是会有一点分不清楚是，就是比较不认识的单词的时候会分不清楚是 R 还是 B。
我尽量我会做到做更好。还有吗？还有什么？什么呢？就说呗。就现在骂老师的话，老师不记得。你可以放心的骂，指着第一句话就行。有什么可以说？瑞姐，你有什么说？没什么说吧？就是有什么老师能说可以帮你理解这个？因为我知道你们是有点痛苦，是吧？就是听不懂，师承就是有一部分一半听不懂啊，能做什么？
就是我有时候就是黑板上在上课，我会找到是在书的那里，因为我看电子书。
是吧？你如果看公式的话，你就那我会多写一些，这个规律是哪里？
对，就是我会找到说是在课的。
这图应该可以看得出来，是吧？图应该可以看得出来。哦，那我就多写一些，就是在书里面哪一页是吧？还有呢？一个。啊？佳姐，
我没有什么太大的。
你们几个呢？是吗？是吧？声音还够大吗？还可以是吧？行。没办法，这课本里面东西就是这样，是吧？如果这是一个英文课的话，就是讲英文课没有意思，是吧？这是你们常见的东西。就是如果你们要做就是腐蚀性测试，你会做吗？你会做到腐蚀性测试吗？不会是吧？那待会儿我们谈到跟你相关的东西，你就听，只要在这里。现在我们学生用这个东西用法更快。So this is an equation, okay, that characterize high torque. Okay? 就是我们的那个 potential stat 是吧？它算出的腐蚀数据是根据这个公式来算的。Okay? This has a name, okay? This is the stern.很像这个人就开了一家公司，专门做这个 potential stat. Okay, so we finished talking about corrosion, okay? So this is this page 386. Okay. So now we're going to talk about mass transfer effect. Okay. So for example, okay, in cases with oxygen reduction, okay, so we have a metal, right? And on top of this metal, there's a layer of salt. Okay? And oxygen has to permeate the salt, right? And dissolve into the salt before it can get in contact with this metal. Right? So O2 gets in here and becomes SO2, right? Becomes solubilized oxygen. That's what that means, okay? I shouldn't say I should call it O2 aqueous, okay? O2 aqueous. Okay? So SO2 is the solubility of oxygen. Okay? This is low because O2 is non-polar. Yeah. Right? Okay? So the oxygen is non-polar, right? So in water, right, is polar. So because it dissolved in a non-polar substance into a polar substance, the interaction is weak, okay? So your solubility is low, okay? So reduction of oxygen, of O2, okay, can be limited. By mass transfer. The surface. So we in chapter 3, right? Chapter 3. Chapter 3. Derive I as a function of potential. Okay. And so, and then we have the mass transfer limit case. Okay? Okay, so we have this case. Okay. Initially, at t equals to 0, okay? At t equals to 0, we have CRS is equal to CR, okay? So this is CRS, this is CR, okay?
the curve.
Okay. So at t equals greater than 0, okay, the CRS is going to come down. Okay? The concentration of R at the surface, right, at t greater than 0, right, is going to start reacting and get turned into the oxidized species, right? So CRS will come down to CRP. Makes sense, right? So the flux of R, okay? The flux of R, right, is equal to the mass transfer coefficient times CRB times CRS. So at t greater than 0, right? CRS starts to react. Okay? And so CRS decreased. Right? The concentration of CRS decreased. Yeah, because this reaction is going forward, right? So over time, right, CRB, right, well, I'm sorry, CRS decreased to stable or to a steady state concentration. Steady state. Steady state concentration. Okay? So at time greater than 0, right, when this reaction starts to occur, right, when this oxidation of PCR reaction starts to occur, then over time, once you reach this equilibrium, right, concentration from the bulk to the surface will appear like this. Okay? 就是在 T 大于0的时候，是吧？这个表面如果这东西开始反应的话，从电极到就是它的水的那个泵离电极远就是远一点的距离的话，它的这个什么浓度几乎呈现这个形象，是吧？就是多少这些 CRB 到了这个电极以后，它就被消耗，转换成这个oxidized形式。Okay. So at equilibrium, okay, the concentration profile for the CRS and COS will be like this. Okay. So at steady state, right? So at steady state, rate of mass transfer to surface will be equal to the rate will equal to the reaction rate transfer. Reaction rate at surface. Right? 对吧？到一个平衡点的时候，这个梯度从一开始就是开始下降，到一个平衡点，它就不会变，它就是这个形态，对吧？它浓度梯度就是这个形态。它已经到一个平衡点这个平衡点呢，就是表面反应的速度是等同于就是 CRE， 就是通过这种扩散的方式到达这个电极的表面处，也就是这个叫 flux。So using the table expression, expression applies. Therefore, expression applies. So I is equal to I naught So this I, right? This I is a function of Rs, right? The current density at the surface is a function of the surface concentration of S, right? Only when only when the species R gets to the surface can you react. Okay? So this is why the surface, the current density is a function of S. Okay? For CRS. Okay. So I is equal to I naught reference C1 over C1 reference gamma 1, which is equal to I naught reference C1 surface C1 hole. So you put this I naught is equal to I naught reference times C1 that's with C1 hole. Okay? So you put this right here. Okay? So then this becomes I is equal to I naught reference C1S C1 hole. Okay? Here this we're going to call it CR and CR reference. CR. Okay? So this CR hole. CR that's CR. CR reference. CR. CRS. CR hole. CRS, CR hole. CRS, CR hole. Okay. So CRS, CR hole times exponent alpha A F S. So we have another equation now. So I is equal to NF and R. Okay? This is another definition, right? The current density is equal to the electron numbers times the Faraday's constant times flux. Okay? So this N right here put here, okay? So we get N F K M C R E C R S. Okay? B here stands for bulk, right? S here stands for surface. Yeah? So now we have two equations. Okay? Equation 1. This is equation 1. And this is equation 2. This is equation 1. This is equation 2. Okay? Yeah? And both this have like the concentration of R at the surface of the electrode 啊，这个浓度不好算，就是不好测，是吧？所以我们想要做的是，就是我们现在有两个这个东西，一个是它的反应速率，就是倒推出来，就是通过热力学方式来推导出来的这个公式。另外一个呢是它的那个什么它的传输现象，根据浓度梯度推导出来的公式。这两个左边都是电流密度，是吧？但是这两个电流密度的这个公式里面都有这个 CRS， 这 CRS 是这个反应物在电极表面的这个浓度，这浓度很难测，所以我们想要把它去除掉，是吧？才可以得到一个比较好算的东西。这 CRB 是 bulk concentration， 这就是我们电解的浓度，我们知道的浓度，是吧？这个是就是 mass transfer coefficient， 这个是 number of electrons Faraday constant， 这些东西我们都可以算 ，temperature alpha A， 这个是它就是我们要么是fix I， 要么是 fix potential， 是吧？这两个东西是选一个另外一个东西就会变，所以我们现在有两个equation，我们想要把这两个equation里面的 CRS 给看出来。So we want to eliminate CRX, okay? And solve for the current density, okay? So I move this to the other side, okay? And F Km is equal to CRB minus CRS. So we get CRS is equal to CRB minus 1 over N F Km. Okay? So using this equation, we put this CRS here. Okay? So we get, and then we get I is equal to I naught reference, or I naught bulk. Okay? I naught reference is just I naught bulk. Okay? I naught bulk. CR. Put this here, this here, right? CRB minus 1 over NF Km over CRB exponent alpha AF DS over RT. So this is 3.32. So move this over. So this is this CRB over CRB minus, what is it, you multiply this in, right? Minus I naught B. I naught B times this is on, right? This is on. Okay, so this is on. Okay, this is on. Okay. I naught B times I. Over NF KM CRB. So I is equal to that. Divide this over, you get exponent alpha A F X over R. Okay. So you got this expression now. So the CRB over CRB, this cancel, this is 1, right? You're left with this expression. So you get I over exponent alpha A F over RT is equal to I naught B minus I naught B times I over NF KN CRB. So you get I naught I times, you factor this is I, right? You gather the like terms, you get I is equal to I times 1 over exponent alpha A F ES over RT. So this minus, move this over as plus, right? Plus I naught B over NF CRB is equal to this I naught B. Okay? So I is equal to I naught B over I naught B exponent alpha A F plus I naught B. You multiply this term with I naught B on both top and bottom, right? So both top and bottom is the same, okay? So I naught B over NF KN CRB. So this cancels. You get I, therefore you get I is equal to 1 over 1 plus I naught B exponent alpha A F RT plus 1 over NF KN. Okay. So I is equal to that. Okay? So this is the kinetic component. And this is the mass transfer component. Okay? we'll stop right here. We'll continue